of you who don't know me, I'm Professor Pat Wheeler from the University of Nottingham. I'm going to give you a very, very brief introduction to where Nottingham is and what we do, but obviously the main part of my talk is talking about some of the research we do, looking at power electronics for electrical power systems. But I thought I'd start with geography rather than power electronics. So Nottingham is here, so this is the United Kingdom. London is down here in the southeast of our country, and Nottingham is in the middle. When you're in England, it is impossible to get any further away from the sea than you are in Nottingham. But it's not very far, it's about 80 kilometres. So we're about 180 kilometres north of London, in the middle of the country. We're famous for a number of people. Some of you may have heard of this character, Robin Hood, and may have heard of the Sheriff of Nottingham in the Tales of Robin Hood. People seem to associate him with Kevin Costner these days. But so Robin Hood didn't actually live in Nottingham. The Sheriff of Nottingham lived in Nottingham, and Robin Hood was just the outlaw that was causing him lots of problems to the north of the city. But the city likes to think of him as the very famous son of the city. I belong to the Power Electronics, Machines and Control Research Group at the University of Nottingham. And we work in a number of different areas. So we look at power electronics and power electronic converters for aerospace and energy applications. We look at energy management systems. We look at electrical machines, both motors and generators. And we look at the applications that they go into. So particularly looking at the future electrical energy networks and renewable energy, and that will be the topic of my talk today. But we also look at applications in aerospace, in electric vehicles, in electric ships and boats. We also have a lot of work still going on in industrial applications, so industrial motor drive applications, and a few specialist areas, including high energy physics experiments. So we look at power converters for places like CERN and Los Alamos, where they're doing work on particle accelerators and so on. But it's the first two of these areas, the future electrical networks and the renewable energy, that I'll be looking at today. We've got lots of people at the moment. We have about 135 people in the research group. So we have 17 members of faculty, academics covering areas of power electronics, electrical machines, motor drives, and so on. And then we have about 50 contracted postdoctoral research fellows and about 70 PhD students within the group. So we're a very large team of people all working on power electronics and the applications of power electronics. To feed all those people, we need lots of money, and at the moment, we have a research grant portfolio of about $35 million US. About half of that currently comes from the European Union, and if you follow the news, you'll know that in about 2 years' time, the UK is going to leave the European Union, so we need to think about how we're going to replace that money in the future. But there'll be ways of doing that. What I really want to talk about today is about high voltage DC applications. And when we're looking at this, this is looking at ways of getting renewable energy onto land and to where people want to use that. And so when we're looking at electrical energy and electrical energy generation, 200-300 years ago, people used to go and live next to the source of energy. So they would build their mill next to the river, and they would live there. Today we build cities where we want to live, and we have energy sources that can be a long, long way away from where we're living. So we need to transport the electrical energy from where we generate it to where we want to use it. And when we're trying to transport electrical energy over a large distance, there's different ways of doing that. We can do that with AC, which is the traditional way. So if you look at the electricity grid in Chile or in the UK, you'll find you have an AC network of high voltage cables that enables the country to transport electrical energy from where it's generated to where it's needed. Now the advantage, so that's sort of typical AC pylon. The advantage if we go to DC is that those pylons become smaller. And if we go under the sea, which is something we have to do around Europe, we find that actually there's a cost benefit. So when we're looking at transmitting electrical energy from where we're generating to where we want to use it, we find that there's a cost to building the stations where we want to actually transmit the energy from and to. And when we look at DC systems, we find that initial cost of the converter stations is very high. Power electronics is more expensive than transformers. Copper and steel is relatively cheap compared to silicon devices and all the complexities we have with power electronics. So when we look at an AC station here, which is basically a transformer, it's very cost effective. When we look at a DC station with all the power electronics I'm going to talk about in the next 20 minutes, we find that that becomes more expensive. But the cabling that I need and the pylons I need for the DC system are cheaper. So when we look at the cost here on the vertical axis against the distance I'm transmitting that electrical energy, I find eventually there's a break-even distance where it's actually cheaper to transmit the electrical energy as DC rather than AC. And at the moment I find that on land, that's a distance of about 800 kilometres, about 500 miles. Okay, now in the UK, that's taken me from Nottingham to beyond the extremes of my country. Okay, but if I look at transmitting electrical energy across Europe, I'm within that distance. I'm going to be over here somewhere. If I look at transmitting electrical energy across a sea, so I need to put cables on the bottom of the sea. Putting cables on the bottom of the sea is very expensive. And so rather than being 800 kilometres as the break-even distance, it's just 50 kilometres. Very short distance. So if we then look at what we're trying to do around the UK. So this is the United Kingdom over here, and this is Northern Europe. So we've got Germany here, France down here, Norway and Sweden and Denmark. My colleague here comes from up here. And what we're trying to do in Europe, Europe is a very highly populated place. In the UK, we have about 65 million people, okay, on this very small island. I don't know how many people live in Chile. I'm not sure if Chile knows how many people live in Chile. But it's a lot fewer than we have in the UK, and you have a very large country. So you don't have quite so many problems that we do. And when we try and put in wind farms or even photovoltaics in the UK, we find we haven't got very much space. We haven't got very much land where we can do that. So what and this is the same for the other European countries. So what we're looking at is actually putting wind farms out here, out in the sea. We can do that because it's a very shallow sea. Okay? There's a continental shelf comes out here, and so that sea is actually relatively shallow. So we can actually put wind farms out at sea and bed them down into the bed of the sea. So that's great. I'm generating electrical energy here, 100 kilometres, 200 kilometres off the coast of the country. And then I have to get that electrical energy back onto the land. If you remember that graph I just showed, that means I'm going to use DC cables under the sea. The other thing we'd like to do in Europe is to start trading electrical energy between countries. Some countries, particularly down in the south, have very good prospects for generating solar energy because they have good sunshine. Those of you who know the UK know that our weather is more like it was in Carico yesterday. Okay, not like today. So it's wet, it's cold during the winter. So it's not such a good place to generate electrical energy with solar, but we do have some wind in the same way as you do in the south of Chile. So here's a bit of a thought picture on connecting up Europe, generating electrical energy in the south of Europe here using photovoltaics, in the north of Europe here, using wind farms, using wind energy, and connecting all those countries together with high voltage DC networks. So rather than point to point, this is a network where we can connect into lots of countries and trade electricity between those countries. So you end up with a concept like this, where we have various transmission and distribution systems, the existing networks in our countries. We have some AC to DC converters. We have a big DC bus around Europe. And then we have various offshore wind farms, various PV, solar plants in the south. And we connect them all together in this DC transmission system. Only two problems with doing this. Well, maybe three. One, we've got to make power electronics reliable and cost-effective. Okay? So that's a technical problem. We're all great engineers in this room. We can solve that one. The other two are slightly harder. The second one is cost. It's going to cost a lot of money to build this infrastructure. So our politicians have got to be able to invest in the future. Lots of money. Okay? Billions and billions of euros. So can they afford to do that? Well, hopefully, if they really want to have renewable energy as the primary source of energy in Europe, they're going to have to do that. That's fine. The third one is political. You've got to get all these countries to agree to invest, to work together to do this. And just to give you a small idea of the problems, of course, the UK has just voted to leave Europe. So we're going in the wrong direction. Okay? So this is a problem. And this is the biggest problem to solve here, is probably the political cost is going to be the most difficult one. But if we want to have renewable energy resources and we want to have security of supply, we need to do this. Now, what's the relevance of this to South America? Well, you have lots of countries in South America. You have different resources in different countries. Could you imagine connecting up the whole of South America like this? With a DC network, so you could trade electrical energy. It's possible to do, but again, you would have the problem of the politics between the countries of actually trading and building that infrastructure, justifying the cost, and so on. But in Chile, I can imagine you having a DC cable running up the country because you have hydroelectric in the south, you've got fantastic potential for solar in the middle and in the north of the country. And I can see how there you could start to trade electrical energy up and down the country, probably a lot more efficiently with a DC network than with an AC network. So if we just go back to my European example, this is what we're trying to do in a picture. We're trying to generate electrical energy using wind farms out at sea. We'll then have a platform. Ironically, we'll probably be using old oil drilling platforms to actually put the power converters on out at sea. So we're replacing drilling for oil and gas with the infrastructure we need for the high voltage DC. And then the high voltage DC cables come under the sea, up onto the land. We need another power converter station to connect to the existing AC grid. Wouldn't it be great if this was DC, but I think it's too far to change all that. So this is the kind of thought picture we have. Generating out at sea, collecting all that electrical energy together onto some sort of platform, transmitting that under the sea. This is about 100 to 200 kilometers, and then back onto land. This is great news for power electronics engineers because some of the most expensive and difficult parts of that system to buy are the power electronics. I can go and buy a wind turbine today. I can go and buy the transformers I need here today. If I want to buy these, I need to think 10 years ahead. And so the people who are doing the procurement for these systems, and these are gigawatt systems, I think the first plant that we're trying to commission is going to eventually be about 5 gigawatts, 5 or 6 gigawatts. It's the size of a large nuclear power station. Okay, so large amounts of power electronics going into that. So people are looking at how to build these power electronics. As with everything, it's not new. almost 50 years ago, people started building a link across the channel between England and France with a DC connection so that England and France could trade electrical energy. And they did that using thyristors. Okay, so devices that were line commutated. And so you ended up with a power converter that looks like this. So you've got an AC system over here, your DC connections on this side, big thyristor connections, and big transformers. It works. It's worked for many years, and about 5 years ago they refurbished it with new power electronics and so on, so that it would work into the future. Problem with thyristors is that you have to wait for the current to get to zero before you can turn them off. It's all line commutated, so you can't start a system when there's a blackout. So when France had a big failure of its power system a few years ago, we had to just, in the UK, we said, sorry guys, we can't help you. Because until they had voltage on their system, we couldn't transmit power across the channel. They had to black start themselves. So it has some problems. There's also a problem with the way you reverse the power flow, because when you reverse the power flow, you have to be careful with the cable type, so you actually have to change the connections around. So it works. It transmits electrical energy, but it's difficult. It's also big. Just to give you some idea, this is the conventional HVDC power system, and you've got a very, very large area here that's taken up with that technology. This is what we're looking at building in the future, and this building here is about the size of one of those halls on that conventional system. The reason for that is when you're using thyristors, you're switching slowly, so all your filters become very large. When we're switching more quickly, when we're using modern power electronics, things come down in size. Okay? And so that's where we would like to be. We always like our power supplies for our computers and our mobile phones to be small, and it's just the same when you get to HVDC. You want it to be as small as possible. The reason for that is you want to build these stations in areas where land is expensive, and particularly in Europe, and so the smaller the footprint, the better it's going to be in terms of the cost of the land and the impact you have on the people around you. So the way we do this is with modern power electronics. I think anybody in this room who's done any work on power electronics will know this circuit here. We certainly saw it a few times yesterday, which is the standard voltage source inverter. And with a standard voltage source inverter, we can switch quite quickly. We can filter with nice small filters, and we can do a lot of work with that. Now, this has a problem when I have a very high voltage here, because these power semiconductor devices only operate at a maximum of 2,000 or 3,000 volts. And I'm going to want to have a DC link here of maybe 200,000, maybe even 500,000 volts. So I've got to do something to be able to increase the voltage capacity of my circuit. And there's a number of ways of doing that. The first thing to do is to put lots of devices in series. So if each device can only block 1,000 volts, and I put 100 of those in series, I've got to 100,000 volts. The problem when I do that is I have a very big voltage step to switch through. The other thing I can do is to go to multi-level converters, and we saw some of these yesterday in the talks. So we can actually go to things like the neutral point clamped converter, and the cascade H-bridge converter, and the flying capacitor converter, and we can start to get multi-level waveforms. Or we can go to these modular multi-level converters. I'll talk a little bit more about these in a moment. But the advantage that these two sets of converters have is I have a multi-level stepped waveform. It already looks more like a sine wave than the output from my voltage source inverter. So my filtering becomes smaller, my losses become lower, and so on. So if we look at these all in a little bit more detail, the first one I can consider is the series IGBTs, where I have these lots of devices connected in series. I have to do something to keep these all sharing the voltage equally. There's a whole set of literature around that, and I get these big steps of voltage. So I have high switching losses, and I have large filters. So where have we gone with this? Well, we started looking at the concept of having lots of converters in series rather than the idea of having lots of devices in series. And this gives you the converters that are referred to as the modular multi-level converters or the chain link converters. And you can think of this as creating a series of stepped voltages. I can control these chain links to give me either a positive voltage, a negative voltage, or a zero voltage, and then I can connect those voltages up in series to give me a stepped waveform. Okay, so the great advantage of a stepped waveform is I can give a good approximation of the sine wave on the AC network, and using that, I can then control the power flow in the system. The most popular topology that people look at is the modular multi-level converter, the M²LC converter. This was proposed by a professor in Germany 20 years ago, I think now, and a company called Siemens bought all the patent rights for the intellectual property. So it's a good circuit, it works. Siemens, as a big company, obviously knew what they were doing. And each of these chain links can produce a voltage of 0 or the voltage equal to the capacitor voltage, and you can stack all those up in both the positive and the negative limbs to get the multi-level waveforms that you want onto your system. The problem with this is that Siemens own all the intellectual property. They own the rights to this. So we don't work, well, we do work with Siemens, but not on this. We work with a company that was called Alstom. It's now part of GE. And what they said to us is, this circuit's great. We want a circuit that's even better than this because we don't want to pay Siemens money. Okay? They didn't want to pay Siemens for the right to use this circuit. And we want something that's better. So go away and find something that's going to be a little bit better. And so that's what we did. We started looking at some other topologies, some hybrid topologies that would do that job. Now, just to give you an idea of what these power converters are like, this is one we built earlier. Well, not quite. But this is a 10 megawatt test station. This is a power supply that you can go for a walk in. These are people. Okay? So this is power electronics the size of this room. These power converters are big. When you're in there and this thing's turned on and it's working at 20 megawatts, you can feel it. You can feel the 50 hertz. It's a great feeling. Okay? So, and you can hear it because all these converters switch at about 3 kilohertz. So you need hearing protection as well. Okay? But just to give you an idea of the sorts of things that you can build. So we built a small-scale prototype in our labs. We then built a slightly bigger one at about 200 kilowatts. And then Alstom built one at 20 megawatts using exactly the same control platform. I don't know if our friend from Opal RT is in the room. Oh, yes, yes. This uses one of those big stacks of Opal RT controllers that we were seeing on the slides yesterday, just to control all of these devices and all of that system. But this is a small-scale demonstrator. The final demonstrators in terms of power will be 10 times bigger than this, but actually probably in about the same volume because we've worked out how to make things a little bit smaller. So we were set this challenge of make these things smaller, make these things more efficient. How can we get around Siemens' patent? And we came up with two main topologies. The first is the parallel hybrid topology, where we still have lots of chain links in series, and then we have some H-bridges here. Now you're immediately going to say, haven't you got more devices? And yes, I have. I'm going to have to spend more money buying IGBTs or IGCTs to build this converter. But I've got some advantages with this converter. The advantages I have are in the efficiency that I can get from the converter and in the way it can control both AC and DC side faults. And that's quite important. So that was the first topology we looked at. If there's a parallel hybrid topology, there has to be a series hybrid topology, and we looked at that one as well. So here I've got some switches, here I've got a lot of chain links, and what we do is we use these chain links here to create either a positive voltage, or down here to create a negative voltage, and then I use these series switches to switch between the positive arm and the negative arm. So I'm alternating between using the positive arm and the negative arm of the converter to get myself a sine wave at the output of that converter. So that's the series hybrid topology, or the alternate arm converter. So we can look at those, and that works. And then the final one we looked at is a sort of combination of using series bridges and parallel bridges and putting those together in a converter. So I've got some series bridges here, some parallel bridges here, some series bridges here. I've still got my main H bridges here. And by doing a combination of these series and hybrid technologies, maybe I can get some benefits. And we find we can. This goes back to what Graham Goodwin was talking about yesterday in terms of active filtering on a power system. By having these two sets of bridges, I get another degree of freedom, and I can start to clean up some of the harmonics on the system and to get better quality waveforms and therefore better use of the infrastructure. So that's all very well and good. We can look at these different topologies and we can write papers about them. We can put some patents in to protect the intellectual property. At the end of the day, we've got to compare them. And this is the bit I like as a professor, because I get to show off this table, which about 10 of my researchers have spent about 5 years creating. Okay, it's the great thing of having an overview of lots of people's research. So we can look at things like the two-level converter, the modular multi-level converter, our series hybrid converter, our parallel hybrid, and the combination. And we can start to look at what that means in terms of things like the losses, in things like the harmonic performance, and in things like how many semiconductors and capacitors I need to buy. And then I need to look at the applications and decide which of these factors is most important. And what you soon realize is that different topologies will be used in different applications depending on what is important in those applications. Particularly down here when we look at the ability to suppress DC faults, so that a DC fault on the doesn't get reflected onto the AC side of the grid. So here we can look at that particular issue. Here we can look at what happens in terms of the AC performance, what happens in terms of the efficiency, and what happens up here in terms of the number of semiconductor devices I buy. So this is all normalized to unity around the two-level converter, and you can see here how they're getting more expensive. But some of these systems that are more expensive have lower losses. We have lower losses, then I'm burning up less energy. I'm selling more energy to my customers. And so I might not care that it's going to cost twice as much to buy that power converter, because I'm going to have half the losses, and therefore I'm going to be able to sell more energy to the customers. So it's a fantastic field to work in. It's fantastic to look at these different topologies, to simulate them, to build them in our laboratories, to test them, and to transfer that knowledge into industry. That's the sort of work we end up doing in this area. And what you soon realize is that if we're going to transmit electrical energy around a country, if we're going to use different sorts of renewable energy, then power converters are going to be an essential part of that electricity grid. Renewable energy sources, be it solar or wind, are not directly compatible with the AC network we have at the moment. That's great news for all of us as power electronics engineers, because we're going to have plenty of work over the next 20 or 30 years working out how to connect all this renewable energy to the grid. So that's good news. But there's challenges. The cost of purchase and the cost of losses is one thing. Reliability and availability. With all these modular multi-level converters, I can put lots of fault tolerance into the converters, but how much do I need? how reliable are the power electronics going to be? And when I start looking at the regulations on the electricity grid, they're all based around old-fashioned technologies. And we really have to work with the power systems people to make them understand that regulations are going to have to change. The way they control the grid is going to have to change if we're going to do this. So thank you very much for listening. I hope you've all found something in that talk. That is not me riding that motorbike, but it is an electric motorbike that goes at over 300 kilometers an hour that's built in my laboratories. Good use of electric vehicle technology once you've got the electrical energy from the wind farms into the grid. Thank you very much for listening.